Hi, everybody. It's a real privilege to speak about after such an experienced group of people. And even though I'm probably a couple of minutes short, I surely hope that you're scared enough by now and you know that you need to protect yourself. So I'm going to have to tell you how Armo will help you with this. And today we'll talk about taking Kubernetes cluster from unprotected state from zero trust using Armo technology. So first, can you give me the screen, please? Still can't move the slides.
You have control now, Leonid?
Let me try. No. Okay. So first of all, let me tell you what zero trust means to us at Armo. What hackers are looking for and how do we protect against that? And you've heard a lot of examples about the very high-profile attacks and what hackers did and how they managed to get into your system. But the bottom line of it is it's always about software. Nobody's going to stick his finger into your cloud and scrub a few bytes. That's not going to happen. They will always either use software in an appropriate way or inject malicious software or change the software configuration, and software will do all the damage. And therefore, the way we'll approach this zero trust in the cloud environment is making sure that we can protect the software and protect the software configuration, ensuring that it does what it's supposed to do, it doesn't do anything else. Still doesn't move. Okay. So how do we know who is calling our APIs and who is reading our data? Because this is essentially what happens in the cloud. Nobody does anything else. The software is running in unattended environment. It runs, it communicates, it reads and writes the data. Nothing else happens. So there are three keywords in this statement. One is who. How do we identify the software? How do we know that software that's calling our interface is the one that it's supposed to call it? How do we know that software is reading our file is the one that's supposed to read that file, whether it's authorized and also whether it's healthy or not? And this is how we address this in Armo product. We have built a technology that allows us to generate something that we call the software DNA, which I'll elaborate in a second, which can uniquely identify every piece of software running in the cloud environment. Once we have the software DNA, we can know who we are talking to, who is calling us, and who is going to read our data. And therefore, we can decide whether we want to answer the call or whether we want to decrypt in the sense of files, decrypt appropriate information that the application is asking for. Software DNA is really a unique technology that we have developed that includes multiple elements in it. Basically, cryptographically digests executables, shared objects, Pythons or any scripts, configuration files, environment variables, command line parameters, and all other parameters that can basically influence the behavior of the application. As I said, the application is designed to do something and it should not do anything else. So all of that is done without any changes to your existing containers, any changes to your existing architecture, and basically can be applied to any type of the software, whether you bring piece from the open source or you develop it yourself or you get it from the third party. It's all aligned and it gives you a unified way of controlling your system and controlling the software running in it. ArmoGuard is a shared library which is automatically attached to every workload that goes up in your Kubernetes environment, and it's done using Kubernetes integration that we have implemented, and I'll show you that in a minute. So what happened is when we want to allow one application to talk to another, or pod A to talk to pod B, the intention is to say that legitimate application running in pod A can communicate with the server running in a pod B. But the reality is different. In reality, any software that managed to inject itself into the container, whether it's done by replacing container at the repository as somebody described before, whether it's done by using vulnerability exploitation, remote command execution, or anything else, arbitrary code execution. It would allow the malicious code running in the same container to inherit all of the rights that were legitimately given to the application itself. Okay, and those rights are declare themselves in two different ways. The one way is the API over the network, which allows them to make any calls basically, and the other one is access to files or data or secrets. As you know, Kubernetes secrets are stored as files, so file and secret is basically the same thing. So what Armo would do, what Armo Zero Trust would do, is basically prevent those malicious activities and identify potentially malicious code that is running in the application, because any attempt to change that code, any attempt to alter or complement it with something else will break the DNA and will immediately identify this. And I'll show you a short demo how it all works. So, Leor, can you please give me this screen sharing capability?
Yes, of course. Okay, so I'm stop sharing and you can share now.
Yes, give me a second. Can you see it?
Yes.
Okay. I'll show you how Armo works on the example of online boutique application, which is an application developed by Google to demonstrate the advantages of microservice architecture and capabilities of Kubernetes. This application is publicly available on the GitHub. Everybody can look at it. And there are several reasons why we picked these particular applications to actually demonstrate Armo capabilities on. One of them is it's not ours, so it basically gives us much better credibility. The other is this application is really a microservice concept, and it includes services developed in many different languages, many different technologies. You can see here applications developed in Go, C, C#, Node.js, Python, Java, etc. It's even one of the previous versions had Ruby on Rails in it. So this application is running now in my let me hide this for a second. This application is running now in my GCP account, and you can see this is the front end that basically how we can interact with the application. This is my GCP account, and you're going to see a lot of command lines in the next couple of minutes. But on the other hand, what I'm showing you is not just a demo, or it's basically the real case where how the application is going to be protected by Armo solution. So first thing we do is we need to register the application in our system, and that is done by registering a cluster. So let's call it ZT demo. Okay, all we need to do is to run this command line inside the console, and now Armo is being installed in the cluster. And in a second, we will see what is being displayed by Armo console immediately after the installation. Again, we've started from this picture. Okay, this is how Google pictures it. Okay, and now let's see how Armo sees this this deployment. Okay, it's going to take a few more seconds. It's always tricky with the screen sharing, but here it comes. Okay, the microservices in the cluster that we called ZT demo is now appearing on our screen. And what we basically see here is the list of services that we have that were part of this application of online boutique application. that are running in Kubernetes cluster. This picture is drawn because we have queried the Kubernetes API, and this is what we have received back. At this point, there is no protection. There's only information about this application. Now, next thing we'll do is go and add one more service, which I will use to show you how the zero trust capabilities work. So it's going to be very fast. Okay. This service will appear in a second on this screen as well. And this is how we know that we have everything. Okay, that's here. And this is how we know that everything is installed in the cluster. We can still use the application, but there is no protection in it. The first step we need to do is to make what we call a discovery step. It's basically attaching Armo to the namespace and starting to map everything that happens inside this namespace. What happened at this point is Armo components that were installed in the cluster communicate with Kubernetes and attach Armo guard to every workload that is running in that cluster. That caused Kubernetes to restart the workloads, and the Armo guard appears inside them and starting to communicate back the information so that we can start mapping and understanding what happens in those workloads. There's no, workloads themselves don't know anything that happens inside them. And all the information that's being reported is basically stored in our backend system and is being analyzed so that we can create what we call identity profiles of that. And you can see we already start seeing some information. We start seeing reports of actual communication channels that happens between the workloads. Okay, and give us a few more seconds and we'll start seeing more information in there. Basically, every workload will become blue, which means in our visualization tool, means that we are attached to these workloads. This really happens in the real time. This is exactly how long it takes to apply Armo to your system. So we'll stay with this for a few more seconds. They're still in transition. Okay, more of them become attached. In a second, they all will be attached. So let's give it a few more seconds. Now, the attachment means that we can now go to inside of this workloads and see what happens inside. What we're actually mapping in them. You can see all the execution parameters of the workload, but the most important ones are the processes that are running in there, the shared libraries that are running in there. These are the shared libraries that are running in there. All the execution parameters such as privileged capabilities, etc. We can see all the files that these workloads are opening. We can see all the inbound and outbound connections that they're making, etc. So basically, this whole thing is giving us the map of what happens inside the workload. And now we are completely attached to the namespace and we can see everything that happens inside that system. Who talks to whom, who is running where, what each workload contains, etc. So our next step is going to be to sign these workloads. Everything I'm showing you from the user interface, it's also possible to do through the API and the command line tool. So you can basically automate everything that happens in there. There we go. We basically we sign all of them. And what happens now, the signing request is being sent to our backend, and we start taking this workload identity profile information, digesting it and creating cryptographic signatures, and then delivering those signatures to every workload in the system. Again, this happens in the real time. This is exactly how long it takes to do this. So let's give it another minute. The digest includes, as I said before, all the executables, shared objects, and other script files, etc., that are running inside that workload, and creates a cryptographic signature of them. The ArmorGuard uses this information in order to validate every workload continuously throughout the entire execution session. So if your workload runs 24/7, we'll be checking it 24/7. We'll be making sure that whatever runs in your system is what you meant to run, and it's nothing else is in there. If somebody tries to exercise this type of Apache Struts attacks or anything else with remote code execution, with arbitrary code execution, with SO injection, etc., we will be able to identify this immediately, and therefore the attack will be prevented. The most important thing is that if somebody has administrative credentials to your system, whether they've broken them through some inappropriately configured interface or just stolen them from your administrator, it doesn't really matter, they will be able to insert additional code to your system. And it's important thing to say is that whatever additional code is going to run in this environment or being able to communicate with this environment won't be able to cause any damage to the system. And I'll show you in a minute why. As you can see, most of them appearing to becoming assigned. Okay, this icon means that the workload is signed. And in a few seconds, all of them will be signed. So we will be able to show what happens inside, how we define policies, etc. Okay, bear with me for just a few more moments. Okay, there we go. Now everything is signed, so we already know everything that runs in that system. So next thing we're going to do is we're going to go and see still all the workloads that are running in the system. We see all of them. Oh, one of them is still terminating. Let's give it a second. Okay, it's done. So now I want to show you this example that you've seen on the slide, where basically if I'm a legitimate workload, I can communicate, and if I'm a malicious one, I cannot. Now, I'm not going to exploit any vulnerabilities at this point because it usually takes a little bit longer. What I'm going to do is use Kubernetes and the credentials that I have in order to execute into the pod, and basically show you how the attack would have been done from within the pod. Okay, so this is what we do. So we have this BI monitor, which is a application that we have added for this demonstration. This application is a Python application, and it's authorized at this point. So if I will run a Python script that is communicating with the front end, I will get the HTML page that is returned by this front end. Okay, so let's see it a little bit bigger. Okay, but I also have a malicious software or potentially malicious software in this container that's called curl, and I can do the same request to the front end. And as you can see, I'm getting the same result. Now, why does this happen? Because I've signed all of the workloads here, but I didn't define any policy. I actually didn't tell them what to do. So my next step would be to go here and say, okay, let's define a network policy, something that we call the basic policy, which is very, very simple policy, very simple to define. You'll see it in a second. Okay, and this policy will basically tell us that every workload that we have just signed is become a part of the club, become a club member, and they can communicate with each other. So all I need to say is take the cluster ZT demo. We take a namespace called hipster, and we say, okay, everybody who runs in this cluster, in this namespace, can now talk to each other. It's going to take a couple of seconds to propagate. Okay, the policy is being sent. Let's give it a few seconds to process. Okay, I'll go back to our screen. Nothing has changed because all of these guys are legitimate. They're all intact and they're running and keep talking to each other. So what I need to do now is to say, okay, let's repeat what we just did. We're going to use Python, which is authorized application, to communicate with the front end, and we've received the positive result. And now let's take the curl, and we see that the connection was refused by the peer, because now the policy is in effect, and therefore we cannot communicate with this interface anymore, because curl is not part of our identity. Even if this program is in the container, it's still not allowed to be part of to share the identity privileges and communicate with the others. Now, if you look at the attack definition methodologies like Mitre or kill chain, okay, you'll see there's a lot of potential attack vectors on using pre-installed software that was not meant to be malicious, but it can be used in a malicious way. So, for example, curl or wget or all of those utilities that can be pre-installed in many basic images, they can be used by malicious attackers for their own good. And therefore, we need to prevent them from being able to share the authorizations that the primary application in the container has received. Okay, so we now saw how the communication failure works. And the second thing we wanted to see is how the secret access works. So I'm going to take the same script, okay, same principle, okay, and do something that we call the read secrets. As I said before, Python is a valid application, is authorized application, so it's allowed to read Kubernetes secrets. These three parameters, they are Kubernetes secrets stored in Kubernetes in a legitimate way. Now when legitimate application reads them, as you can see, they're on the screen. They're all readable. Obviously, these are not real passwords, so please don't try them on our website. Okay, but now what I want to do is to do a cut, which is an application that usually comes with the basic images. Okay, and try to access the same secret in the file. Okay, the file called, for example, username. Okay, as you see, that we receive a garbage. So we cannot basically read the secret. Okay, let's do something more articulated than cut. Let's take, for example, hex dump. Okay, hex dump. Typing is always good. Okay, as you can see, the secret is not readable when it sits in the file. So application like cut or application like hex dump, which are both part of this container in legitimate way, they cannot read the secrets, while the Python application, which is authorized, can do this. Okay, and this is how we prove that we basically protected both elements. We protected the communication, the APIs, and we protected the files on the storage. It could be in any type of the storage, by the way. And specifically files like Kubernetes secrets, which we have a special pre-integration for. We have a user interface allowing you to pick any secret and say protected. The basic idea here is the application that uses them has no idea that Armo is there and Armo is protecting all of that. It's completely standard or completely unknown to us, third-party application that does what it does. And we have not done any special integration or special development for it. So taking it back to the beginning, what Armo Zero Trust is doing is basically making sure that only healthy and authorized applications can communicate and can read necessary information. And if there is one thing that you take from today's meeting, take this: how fast we could do this, how simple and how DevOps oriented this tool is. You don't need to go and beg your developer to change something in the code and to add the capabilities or start encrypting or decrypting. The DevOps engineer can sit there, get the visibility information that I've shown you, and decide which communication channels should be encrypted, or which files have to be protected, and which software identities have to be signed and verified. You don't have to go and do it on your entire cloud in one step. You can do it step by step. You can use all these features independently or together. And all the granularity of deployment is basically the simplest you can imagine. This is more or less what I had to share. So I'm going to stop screen sharing and go back to Lior.